Year 13 revision, the normal distribution and hypothesis testing. In this video, we're going to have a look at a series of exam questions based on the normal distribution and hypothesis testing. This will cover use of the CG50 calculator, Casio CG50 Graphical Calculator efficiently. It will also look at standardising and different methods for approaching hypothesis tests, so using p-values and critical regions as two possible alternatives. So, in any question, it is always important to make sure that you have read the wording very, very carefully within the question. Now, this particular question very helpfully tells us that the response time, and remember time is continuous, so this is already an indication that this is going to have to be modelled by a continuous random variable. The response time may be modelled by a normal distribution. Over a long period of time, it has been noted that 8% of the response times are less than 58 minutes and 19% of the response times are greater than 86 minutes. We then have to determine estimates for the mean and standard deviation of the response time. Now, a key thing to remember is this idea of percentage, probability, and proportion essentially being the same thing, or different ways of expressing the same concept, which is essentially proportion. So 8% of the response times are less than 58 minutes and 19% of the response times are greater than 86 minutes. We're going to convert these statements into probabilities, but before we do that, we need to define what the variable is so that we're clear when we start talking about x or x bar that we actually understand what that is. So I'm going to say that x is the response time in minutes. And the first statement about 8% of the response times tells me that the probability that x is less than 58, so response times being less than 58 minutes, is equal to 0.08. 19% of the response times are greater than 86 minutes. So that gives me two statements here. Now, we are trying to find the mean, mu, and the standard deviation of the response times. When we are in a situation where we don't know mu and sigma, we can't just use the inverse normal function on the calculator because it would ask us to input mu and sigma and we don't know what they are. So in this situation, we have to standardise to the z distribution. So this becomes the probability that z is less than 58, and you always minus the mean and divide by the standard deviation when you standardise, and of course the probability remains the same. The standardisation just shifts this to the z scale rather than the x scale, and we'll do the same over here as well. So remember, z is equal to x minus mu divided by sigma, and we get these results here. Now, whilst it's not a requisite to draw a diagram, it can be a very good way of identifying which tail we are indeed working with. So I'm going to do that. I'm going to sketch two normal distribution curves, and I'm going to mark on the information from each of these. So here we go. This is my z-axis. Of course, z, remember, is the standard normal distribution, which has a mean of 0 and a standard deviation and variance of 1. So here's my normal curve. Quick sketch in both cases. Now in the first example, the probability that z is less than this value is equal to 0.08. That means the region to the left-hand side of this value must be 0.08. So this value here, 58 minus mu over sigma. Now, on the other side, the probability that z is greater than this value is 0.19. So this value 86 minus mu over sigma must have a region that's 0.9 to the right of it. And we can then use the graphical calculator to find out the information that we need. Now I'm going to do this in statistics mode because it's a lot easier to input the correct values this way, and you don't need to memorise the order in which you have to do it. You are given prompts by the calculator. So go into statistics mode, mode number 2 on the calculator, and then you need to select distribution, which is F5. No, you don't need to write this down in an exam situation. I'm just giving you the prompts here for simplicity. So distribution, which is F5. We then want the normal distribution, which is F1. And we're working out an inverse normal here because we know the probability, but we want to know the Z value that corresponds to that. So we want inverse normal, which is accessed via F3. And then you get a whole list of items to input here. Now, the data should be set as variable, and you've got the options F1, F2 to toggle between list and variable if yours is not in the right setting, but it must be set at variable. Now, the tail here for this question on the left-hand side, the tail here is the left-hand tail. The area of that tail is 0.08, and your sigma value is the sigma value for Z, which is 1, and your mu value is the mu value for the Z distribution, which is 0. Make sure you've inputted the values the correct way round, sigma first and then mu. And again, the calculator gives you the prompts, so you don't need to worry about memorising any orders. This then gives us phi to the minus 1 of that value 0.08, which is equal to minus 1.405. So what we have found out is that 58 minus mu over sigma is equal to minus 1.4050 ... And we know that this is going to be a question that involves simultaneous equations, so I'm going to rewrite this as 58 minus mu equals negative 1.4050 sigma. So we'll be able to use this simultaneous one half of a pair of simultaneous equations in a moment. Now we do exactly the same for the other probability, but this time in our settings, the tail is going to be the right-hand tail and the area is going to be 0.19. This will give us the value for 86 minus over sigma, and this is equal to 0.8778 ... So we can rewrite this as 86 minus mu equals 0.8778 sigma. And then we have a second of the pair of our simultaneous equations which we need to solve. So here are my simultaneous equations. I'm going to use the graphical calculator to solve these, but first of all I need to do a little bit more manipulation here. So I'm going to rewrite this as mu minus 1.4050 sigma equals 58, and then I'm going to rewrite this one as mu plus 0.8778 sigma equals 86. Now the graphical calculator has a simultaneous equations solving feature, so we're going to use that. So that is in equation mode, or mode A, so we select that. We then want F1 for simultaneous equations with two unknowns, F1, and then we just input the coefficients of mu and sigma. So I input 1 for the first equation, then negative 1.4050 ... and then 58, and then I input 1 again, 0.8778, and then 86. And this then gives me my values for mu and sigma. So mu works out to be 75.233 ... or 75.2 to 3 significant figures, rounding it sensibly. And sigma works out to be 12.265 ... so 12.3 to 3 significant figures. So on to part 2 of the question. The recovery firm claims that 95% of their response times are less than 90 minutes. Investigate this claim. So we now have a distribution x of recovery times or response times, and we know that it is normally, the times are normally distributed with a mu value of 75.2 and a sigma value of 12.3, variance of 12.3 squared. Now, what we're going to do is work out the probability that response times are less than 90 minutes, and we'll compare this with 95%. So this can again be done in the statistics mode on the calculator. So again, we want F5, which is distribution. We want F1 for normal. And this time we want normal cumulative distribution, which is F2, and we just enter in the values that we want. Now, we're working out the probability that x is less than 90, which is effectively the probability that x lies between negative infinity and 90. So we just need to put in a number that is low enough for us to make sure that we capture the full probability. So I've gone to quite an extreme and put in negative 10,000 here, which is obviously much too large, but it guarantees me that I will get an accurate result at the end. The upper value is obviously 90, and then we input our value of sigma and our value of mu. This gives me an answer of 0.8857 ... which if we convert that to a percentage and round it, that's 88.6%, which is less than 95%. So the claim is not justified. Now notice the mark for this question. It's a 2-mark question, so it just involves a simple probability calculation. This is not asking us to do some kind of extensive hypothesis testing. It's just calculating a simple probability for a comparison. So, example 2. Now, those of you who have watched the binomial distribution and hypothesis testing video will recognise the first part of this question, which is a binomial distribution hypothesis test. So, the context of the question is there is a resident population of pilot whales, and in the past it was thought that 20% of the population were male, and it's now thought that the proportion of males has decreased. Scientists caught and released a random sample of 43 adult whales and found that 3 were found to be male. Calculate a hypothesis test to investigate whether there is any evidence that the proportion of males has decreased. So, this question is a binomial hypothesis test. It's a hypothesis test based on the binomial distribution. Now, how do we know this? We're counting the number of whales. So in this particular question, you might say, y is the number of adult male pilot whales. And you're talking about a number of items. That's not a continuous quantity, that is a discrete quantity. It's going to be 0, 1, 2, 3, etc. So it's set up for the binomial distribution here. So we have y has a binomial distribution, and 43 is your n value, and your probability value is 0.2. So we're not going to run through part 1 again. You can watch the binomial distribution companion video if you want to see how to do the first part of the question, because the second part of the question is independent to this. So previous studies also showed that the mean length of adult females was 2.98 metres. So we're now into continuous territory here. If we're looking at length, that's a continuous variable, a continuous random variable. So this is where the normal distribution will come into play. So on another occasion, so we can see it's a separate situation to the first one, scientists caught a random sample of 39 different adult female pilot whales, so n equals 39. The length x of each of these is measured before it was released, and here is the data summarised below. Now, our task is to carry out a hypothesis test at the 5% level to investigate whether there is any evidence that the mean length of adult females has indeed changed. So, this is another hypothesis test, but it's a hypothesis test based on the mean mu, so this is a normal distribution hypothesis test. So, this time x is the length of adult females, and x is thought to have a normal distribution where mu is thought to be 2.98, and sigma squared are unknown. So that's really important. So the data has been summarised below. Let's see what we can calculate with this data. So the first thing that we can calculate very easily is x bar, the sample mean. So this will give us a test statistic that we can use. So x bar is of course equal to sigma x over n. So that's going to equal 120.7 divided by 39, which gives us a value of 3.094 ... and I would save that in a calculator memory. For the moment, I'm going to just leave it unrounded and keep it in a calculator memory ready for use later on. If you want to round it to 3-4 significant figures. Make sure you have enough accuracy to follow through the rest of the question with. Now, the next thing that we're going to need to do is work out the standard deviation for this sample. So, our sample standard deviation is equal to the square root of sigma x squared minus n x bar squared, all divided by n minus 1. So let's input the information. So 384.75 minus n, which is 39, multiplied by x bar squared, all divided by 38. And let's work out the sample standard deviation. And this comes to 0.54287 ... And again, I'm not going to round this just for the moment. I'm going to store this in a calculator memory, so I've got it ready for use. Now, because our population variance and standard deviation are unknown, in this situation, what we have to do is use the sample standard deviation as an estimate for the population standard deviation sigma. So we use this as an estimate for the unknown value of sigma. Female. Now, the next thing we're going to do is set up our hypotheses. So H0, the status quo, we think that the population mean mu is 2.98. Now, H1, go back to the wording of the question. It's asking us to test for evidence of a change in length. So this alternative hypothesis is mu is not 2.98. This is a two-tailed test. And we'll decide which tail we need to investigate in just a moment. Now, having introduced this symbol mu, we need to define mu carefully, and we need to make sure we use the correct wording as we do this. Mu is the population mean. We must include that word population there. The population mean length of female pilot whales. Make sure you've used the correct context here and the full explanation. So now, let's have a look at our test statistic again. Our test statistic is x bar, the sample mean, which was 3.093 SF. Now, what we want to do is compare this with the value of mu, which is equal to 2.98, the population mean. So what do we notice? We can see clearly that x bar is greater than mu, so our sample mean test statistic 3.09 is greater than 2.98, which tells us we only need to investigate the upper tail when we calculate our p-value. We don't need to investigate the lower tail because our test statistic is greater than the population mean. So there's no point investigating the lower tail. Now, before we do our probability calculation, we need to set up the distribution of the sample means. So remember our original X distribution, which is a normal distribution where mu is 2.98 and sigma squared, or sigma, are now based on the sample standard deviation. So sigma squared is 0.5428 ... squared, and that's the value of sigma. Now, because our test statistic is x bar, we need to look at the x bar distribution. Now, the mean of this distribution is still mu, 2.98, but but its variance is sigma squared over n, which means that its standard deviation is sigma over root n. So that is 0.5428 ... divided by the square root of 39, and I'm going to evaluate that calculation and I'm going to store that in a calculator memory. So we divide by the root of 39, there we have it. So this gives me a standard deviation for the x-bar distribution of 0.08692, and that's going to be stored in calculator memory C. Notice I write down which memory I've put various statistics in, so it's easy for me to find them again. Now, remember we said that we were going to investigate the upper tail. So the probability calculation that we need to work out here is the probability that x bar is greater than little x bar. So the probability that x bar is greater than 3.09 ... So we can do this in statistics mode on the calculator. We must make sure that everything is set up as it should be. So remember, in stats mode you want F5, you want the normal F1, normal continuous F2, and then let's make sure we've set up the calculation properly. So the lower value is of course our x bar value, and you can use the calculator memories here using the alpha key to draw back values out of the calc memories. Now the upper value just needs to be a very, very, very large number. I've put in 100,000. Sigma, of course, is this value because it's the standard deviation of this distribution. So you must make sure you enter this value here. And our mu value is, of course, 2.98. This then gives me my probability value. And this gives us a value for probability as 0.093176 ... which I'm going to round to 9.3% to two significant figures, and of course we need to compare that to 2.5%. The question asked us to do the hypothesis test at the overall 5% level. It's a two-tailed test, so we only need to compare with half the significance level. So that's 2.5%. It's greater than 2.5%, so this result is not significant, and we need to write that down. Now, I always suggest that you think of 3 bullet points to write at the end. Always think of it as 3 bullet points that require stating. The result is not significant at the 5% level. We do not have sufficient evidence to reject H0. And let's put a third comment in the context of the problem. We do not have sufficient evidence to suggest that the mean length of pilot whales has changed. Notice the use of language here. In the question, we were testing for evidence of a change, and that's what we need to make sure we do in our conclusion, our contextual conclusion here. Now, we're going to have a look at the same question using critical regions as an alternative method. Now, I would, again, make it very clear that the p-values method that we've just used is much quicker and much easier to use than the critical regions method, but nonetheless we might be asked to find critical regions, or there might be a scenario in which we are required to find critical regions, so it's important to know how to do this. So what I'm going to do is start off by sketching the distribution that we are working with. So we're working with the x-bar distribution, which has a mean at 2.98. Here's the curve, and it's a two-tailed test, which means that the critical regions are 2, plural. There's one here, which is 2.5%, or 0.025, and then there's a lower critical region, which is also of the same value, 0.025. Now, we need to find these values here and here, which are the critical values. So if I call that C1, call this one C2. Now the probability that x bar is less than C1 is of course 0.025, and if we use the inverse normal on the calculator, this will allow us to find the value of C1. So again, in stats mode, we want distribution normal, inverse normal, which is F3, and we're looking at a left-hand tail with a region of 0.025. Our sigma value is the standard deviation of the x bar distribution, which we calculated as 0.0869 ... and the mu value is of course 2.98. So the inverse normal gives us a critical value C1, which is 2.80962. Now, we could work out C2 using symmetry, given that this measurement is the same as this distance here. We can also use the inverse normal again to work it out. So the probability that x bar is greater than C2 is equal to 0.025. So again, using the inverse normal on the calculator to work out C2, this time we want to change the tail to the right-hand tail. The region is still 0.025, and this gives us C2 is 3.15037 ... So I'm going to mark those values on my graph for clarity so we can all see them. So C1 is 2.81 to 3SF, and C2 is 3.15 to 3SF. Now, what was our test statistic? Let's go back to that really important value. So our test statistic was x bar, and that was equal to 3.09. Now that's of course in the right hand region, so that's why we only need to really investigate the right hand tail here. So our test statistic x bar is equal to 3.09, and you can see very clearly it's not in the green critical region. Now how would I write that out in a clear way? I would say that 3.09 is less than 3.15, which is of course the critical value. So it's not in the critical region. Now, once something is not in the critical region, this implies that we do not have a significant result. And that gives us the first of our 3 bullet points. We do not have sufficient evidence to reject H0. We do not have evidence that there has been a change in the length of adult female pilot whales. So that's an alternative method in which you can run the hypothesis test, which is perfectly valid, but might perhaps take a little bit longer than doing one probability calculation. Now, you can also run these hypothesis tests with standardisation, but unless you're in a situation where you haven't got mu and sigma, there is no real reason to standardise. So unless you're specifically asked to, avoid the standardisation because it just adds in an extra element of work that you don't need to do, which takes up time that you do not have in an exam situation. So, example 3. Now, this does refer to the large data set in terms of the pre-release data, but we're not going to worry about that because this question can still be answered without knowledge of this particular large data set. So we have information about countries, and data for one particular country, Croatia, shows that the average number of mobile phone subscribers per 1,000 population is this value here. So this is saying that the average number of mobile phone subscribers per 1,000 people in the population is this. And it's interesting because this average is obviously larger than 1,000. So why would the average number of mobile phone subscribers per person be greater than 1,000? Well, have a think about it. People can have more than one subscription. Quite often people will have a work phone and a personal use phone. If somebody has multiple jobs, they may well have multiple mobile phone subscriptions. So it is assumed that once the data have been cleaned, by cleaned we mean removing values that are non-existent, missing values, tidying the data to make sure all of the values are clear. The average number of phones per 1,000 population in different countries can be reasonably approximated by a normal distribution with mean 996 and standard deviation 407. Always write this out symbolically, can stop you from making silly mistakes later on. So part 2 actually does ask us to state 2 ways in which data may have been cleaned. So 2 ways in which this could have happened. We could have dealt with missing data, so perhaps deleted countries where data was missing, and outliers as well. So if it's clear that there are outlier values, then these may well have been removed as well. That's 2 ways in which data may have been cleaned. Now, figure 11.1 shows a box plot of the clean data. Give the name of the measure which the arrow is pointing to. So this should be really, really obvious, even back from GCSE maths, that this is the upper quartile. Use the approximate normal distribution to estimate a value for this measure. Now, the approximate normal distribution, if x is the average number of phones, then x has a normal distribution with a mu value of 996 and a sigma value of 407. Now, because x is calculated as an average value, then we don't have to worry about applying continuity corrections here, because we're not looking at data that's discrete, because once you calculate an average value, it becomes a continuous measure. So we don't need to apply continuity corrections here. Now, what we do know is that for the upper quartile, this represents 75% of the data. So we can say that x, the probability of x being less than this value, the upper quartile, is equal to 0.75. We could also do the probability that x is greater than the upper quartile equals 0.25. This then requires us to use the inverse normal on our calculator. So in statistics mode, on the inverse normal, so we want distribution, normal, inverse normal. The tail that we are looking at is the left-hand tail. Again, imagine a sketch of the normal distribution if you need to. So there's the mean at 996, the upper quartile would be here, and what we are saying is that 75% of the data is covered in the tail that's on the left of the upper quartile. So the tail is the left tail, the area of that tail is 0.75, our sigma value is being inputted as 407, and our mu value is 996. Now, this then gives us the upper quartile equals 1,270.51733, and then we can round this sensibly. It's such a large number, I'm going to round this to 1,271 to 4 significant figures or to the nearest whole number. You can check that on your calculator. So we then move on to the next part of the question, where Fatima thinks that the mean number of mobile phone subscribers per 1,000 population for the countries of the world has increased. So they think that the mean has increased. In order to test this, he obtains some up-to-date data for a random sample of countries and uses software to conduct the appropriate hypothesis test at the 5% level of significance. So let's take a look at the hypothesis test that's gone on here. So look at all the wording, a z-test for a mean. Now the null hypothesis here, h0, mu equals 996, and then the alternative hypothesis, look at the box that's been selected, mu is greater than 996. That's because they think that the mean has increased. And of course, mu is your population mean number of mobile phone subscribers per 1,000. So here's the information that's been collected from the sample. So let's see what this is. The mean is the sample mean, so x bar is 1130, and that of course is your test statistic. Now, sigma here is 407. That's your population standard deviation, and n is equal to 12. So that's the sample size. And here's the result for the z-test of the mean. So you get all of this information back. So the mean here, that's x bar, that's sigma over there. Now this value is interesting, SE, that's the standard error, and that's equal to sigma over root n. So that would be equal to, in this case, 407 divided by the square root of 12. And this is the standard deviation of the x bar distribution. N, of course, is sample size. Now, the z value is the standardized version of the sample mean x bar. So this z value, you calculate it by taking x bar, subtracting the mean mu, and then dividing by the standard deviation of the x bar distribution, which is sigma over root n, or the standard error. So this value would have been calculated by taking 1,130, subtracting 996, and dividing by sigma 407 over root 12. So let's work out what that comes to ourselves, just to understand or get a better understanding of what's going on here. So working all this out, this comes to 1.1405 ... So that's this z value here. So the z value is based on the x bar value. And then what's this here? This is the p value, 0.127. So that number here is the probability that z is greater than the z value of 1.1405, and that's equal to 0.127. You can check that on your calculator yourself. If you go into stats mode, go into distribution, normal, cumulative. If you set your lower value as 1.1405, set your upper value to be a very large number, set your sigma value to be 1 for the z distribution, your mu value to be 0 for the z distribution, and you get a probability of 0.127. So this is a standardized version of the hypothesis test that's taking place here. So if you were to sketch this on the two distributions, you have your x bar distribution, and then you have your standardized z distribution. So in the x bar distribution, the mean is mu, which is 996. For the z distribution, the mean is, of course, 0. And for the x bar distribution, our test statistic is 1130. And what we've discovered is that the region to the right of that, the probability of x bar being greater than 1130, is 0.127. Now, all that's happened in this question is that 1130 has been standardised to a z value of 1.1405, and the region to the right of that is still 0.127. So the probability of x bar being greater than 1130 is the same as the probability that z is greater than the standardised value of 1130, which is 1.1405, ... and both of these are equal to 0.127. So the test could have been carried out in terms of the x bar distribution or the z distribution. It doesn't matter. You will get the same p-value of 0.127. In this particular question, the z test has been run, so the standardised version of the test has been run just as an alternative option. Now, none of this actually answers the question, but it's useful for us to understand exactly what is going on here. The question just says, state the conclusion of Fatima's test, explaining your reasoning. So what is the conclusion of the test? Well, we look at the p-value and we need to compare it to the significance level. Now, if you've read the question carefully, you will notice that there is no significance level given for this question. And in that situation, you need to be sensible and think about a sensible significance level to use. Usually 5% is a sensible one to use, possibly 10%, possibly 1%, but those are the standard sort of measures to use. So the p-value is equal to 12.7% if we compare it to a percentage, which is greater than 5%. It's also greater than 10%, which means that the result is not significant at the 5% level. It wouldn't be significant at the 10% level either. We do not have sufficient evidence to reject H0. And then our third comment needs to be in context. We do not have evidence to suggest that the number of subscribers, the average number of subscribers, has increased. So the crux of this question was really understanding all of the numbers and all of the information in this printout. And that can look very confusing when you see all these numbers, but read it carefully, break it down, and it's all information that we have used before. It's all information that we have seen. It's just a case of making sure you understand exactly what it is. And fundamentally, remember, there is absolutely no reason to standardise when you're running your hypothesis test. You can do the whole thing in terms of X bar. There's no problem with that. The question is just testing whether you understand the standardisation process. Now, there is one last part to the question. It does say with reference to the pre-release dataset, which is a dataset you haven't seen. Comment on the sample size Fatima has chosen. Well, even without seeing the large data set, which contains all of the countries of the world, you can see that a sample size of 12 is very, very small. So it's such a small sample compared with the number of countries in the population, which makes any kind of inference less reliable. So, example 4. A team of biologists are monitoring a subspecies of vole on a remote island. Previous studies have shown that the population mean mass of adult voles is 26.2 grams. That's adult male voles, 26.2. It is believed that due to changes in the environment, the mean mass may have altered. 3 of the biologists conducted a new survey and each collected a random sample of adult male voles. The voles were weighed and tagged and then released unharmed. And here we have summary statistics. So there were 3 samples. We've got sample means, sample standard deviations, variances, min-max values, quartiles, medians. Now where it says count, that's of course the frequency, so that just gives us the n value for each sample. Now, part 1, for each sample calculate sigma x and sigma x squared. So that's the total of the data items, sigma x, and the total of the x values squared. So where do these values come from? Well, they come from understanding how the mean is calculated. So remember, the mean is equal to sigma x over n. So sigma x can be calculated by working out the mean multiplied by n. So we can work out these values for each of the samples. So for sample 1, sigma x is going to equal 22.6 multiplied by 9. And so on and so forth for sample 2 and sample 3. And we can simply work these calculations out and then make sure we've written down our values. Now, how do we find the values of sigma x squared? Well, that relates to understanding the standard deviation formula. So the standard deviation and the variance can be used to find sigma x squared. I'm going to use the variance calculation because that will involve a little bit less work than the standard deviation calculation. And the values for the variance are, in some cases, not all, slightly nicer numbers. So the variance is equal to sigma x squared minus n x bar squared all over n minus 1. Now, if we rearrange this formula, we can say that sigma x squared is clearly equal to the variance multiplied by n minus 1 add n x bar squared. So for sample 1, sigma x squared will equal its variance, which is 8.9, multiplied by n minus 1, which is 8, add n, which is 9, multiplied by x bar, which is 22.6 squared. This can then be evaluated very simply on the calculator, and this comes to 4,668.04. We can do similar calculations for sample 2, where sigma x squared will be equal to 10.618 multiplied by 10 plus 11 multiplied by 22.8 squared, and that comes to 5,824.42. And then for sample 3, sigma x squared will be 16.9925, not such a nice value, multiplied by 16 plus 17 multiplied by 23.7 squared, and that comes to 9,820.61. So, part 2, we now need to use our answers to the previous question to calculate the mean and variance of the mass of all the voles caught in the survey. So, this means that we need to work out our overall sigma x by adding together the individual values of sigma x. So this is 203.4 plus 250.8 plus 402.9, which comes to a total value of 857.1. And then the overall x bar is going to equal this value divided by the total number of voles, which is the total n value, which is 37 if you add those together. So this gives us a value of 23.1648 ... and I'm going to save that in a calculator memory for later use. So we then want to work out the overall value of sigma x squared by adding together the individual values of sigma x squared. So 4668.04, add 5824.42, add 9820.61, and that gives me a total value of 20,313.07. Now, to get our overall variance, we take this value of sigma x squared, we subtract from it the overall n value, 37, multiplied by the overall x bar squared, and we divide by the overall value of n minus 1, which is 36. And this gives us the variance, which is 12.7351 ... or 12.7 to 3 SF. We should round our x bar value as well, now that we're at the end of the calculation, so that is 23.2 to 3 significant figures. So we have our finalised answer for the mean and for the variance. So the biologists used the results of the survey to test at the 5% level the hypothesis H0, which is mu equals 26.1, versus the hypothesis H1, mu is not equal to 26.1. So they are running a two-tailed test to test if there is a difference in the average mass of the voles. So, part 3. Assuming that the distribution of the masses of adult male voles may be modelled by the normal distribution with the value for the variance found in part 2, calculate the critical region for this test. This is an example of a hypothesis test question where a lot of the admin aspect of the hypothesis testing has been done for us. So the hypotheses have been set up, so we don't need to do anything further with those. We have to just calculate the critical region for this test. So we're working with a 5% significance level, and it's a two-tailed test. Now, let's sketch the normal distribution. And I'm going to sketch the x bar distribution. So if x is the mass of adult male voles, we know x has a normal distribution with parameters mu and sigma squared. Now, what's mu? Mu is 26.1. What's sigma squared? Sigma squared is the variance that we worked out in the previous part of the question, 12.735 ... Now, the hypothesis test will be based on the x bar distribution, which has these parameters. So the key thing here is that the mean of the x bar distribution is mu, which is 26.1, but its standard deviation is sigma over root n, which is the square root of 12.735 over 37. So I'm going to work out what that is using the value that we had for the variance previously. And that comes to 0.58667, and I'm going to store that in a calculator memory so it's ready for use in the hypothesis test. So here's my sketch of the distribution for x bar. There's the mu value, normal distribution shape, and the critical regions will be symmetrical regions, although my sketch diagram doesn't look very symmetrical, it's meant to be. There is a 2.5% region or a 0.025 probability in each tail. So the critical values, let's call them C1 and C2, demarking the critical regions. The probability that x bar is less than C1 equals 0.025. So we're going to use the inverse normal on the calculator to find out the value of C1. Now, doing this on the calculator is not difficult. We go into stats mode, distribution, normal, inverse normal again. The tail is set at the left value. The area is 0.025. We must input the correct values for sigma and for mu. So the standard deviation is this value here that we worked out previously. And the mean, of course, is this value here, 26.1. So this gives me a lower tailed critical value of 24.950 ... and that means that this number here is 24.95 there. That's the lower critical value. Now the upper critical value, the probability that x bar is greater than C2 is equal to 0.025, and again using the inverse normal I simply need to set this up for a right hand tail. Everything else stays the same, and this then gives me a value of 27.2498 ... So the upper critical value is 27.24 ... So we have our critical region. Now I think we should state what these critical regions are. So the critical regions are for x bar values that are greater than 27.25 to 2 decimal places, and x bar being less than 24.95 to 2 decimal places. So these values demark our critical regions. Now, Part 4 asks us to state the conclusion reached by the biologist explaining your answer. Well, for this we need our test statistic, which is our value of the overall sample mean x bar, which if you recall was 23.2 to 3 significant figures. Now, is that in one of the critical regions? So, yes, it is. It's in this lower critical region here. If you look at the x-axis, 23.2 would feature here, so it's clearly in the critical region. So how would we write this as a conclusion? We would say very clearly 23.2, which is x bar, is less than 24.95, so is in the critical region. This means we have a significant result. and this means we have sufficient evidence to reject H0 and evidence to suggest or we have sufficient evidence to suggest that the mean mass of adult male voles has changed. So notice the three key components of this statement again. So we have a significant result. We have sufficient evidence to reject H0, and we have evidence to suggest, and that's really important, that use of the word suggest. We're not finding a conclusive result, we've found some evidence to support a claim that the mean mass of adult male voles has changed. And notice, even though we were working in the lower tail, we never say that we've got evidence of a decrease in mass, we've got evidence of a change. Remember, H1 was not a test for a decrease, it was a test for a change, and that is the language we need to use in our conclusion. Let's move on to example 5. So, we're given some contextual information about someone going for a walk. Over a long period of time, the mean time taken to complete the walk was 56 minutes and the standard deviation was 4 minutes. Now, a few months ago, they were ill, unable to complete the walk for a month, and the partner now thinks the mean time taken to complete the walk has increased. Over a period of time, a random sample of the times taken to complete the walk have been collected, and summary statistics have been generated in this table here. Now, it's really important that we understand the information in this table before we get to the last part of the question, where we've got to use information from this table to conduct a hypothesis test to determine whether there is evidence at the 5% level to suggest that the mean time taken to complete the walk has increased. So, the information that we have at the start of the question, let's go back to this. So over a long period of time, the mean time was 56. So we're saying that mu was known to be 56 and sigma was known to be 4. Now, the statistics here on the table are based on the sample. So what is the information in the sample? Well, n equals 19. So that's the number of walks, essentially. The mean is 57.4737. So what's this information? This is x bar, the sample mean, which becomes our test statistic. So we then have two values here, sigma and s. What are they? So you'll notice that they're both versions of the standard deviation, but slightly different calculations. One is larger than the other, and that's because the first one, which has been labelled sigma over here, that is the root mean square deviation, and s, which is slightly larger, is the standard deviation, and both of them are based on the sample calculation here. So they're the sample root mean square deviation and the sample standard deviation. Now, if you've forgotten what either of those calculations are from what you've done on this previously, the root mean square deviation is equal to the variance divided by n, all square rooted, and the standard deviation is equal to the variance divided by n minus 1, all square rooted. Now, for the standard deviation, you're dividing by a smaller number because n minus 1 is smaller than n. And that will, of course, result in a larger answer, which is why the standard deviation is larger than the root mean square deviation. Now, what else do we have? We have sigma x squared, and then we have some information pertaining to the minimum, maximum values, the quartiles and median, which would be useful if we were drawing a box plot, but we're not doing that. So really, a lot of this information has been presented to see whether you, as an individual, can pick out the key pieces of information that you actually need to do this hypothesis test. So all of this will be of no value in the hypothesis test. Useful if we're drawing a box plot, not useful otherwise. Now, do we need sigma x and sigma x squared? No, because the calculation for the mean has been done as well. Additionally, we don't actually need this information about the root mean square deviation and the standard deviation because we actually have the population standard deviation up here, and that's the value we use. We would only need the standard deviation if we were not given the population standard deviation sigma. We would then use the standard deviation for the sample as an estimate for the population standard deviation. So to summarise, the root mean square deviation would never be of use to us, so that can go. The standard deviation underneath, the sample standard deviation, would only be of use to us if we didn't know this, but we have this. We've been given the population standard deviation, so actually we don't need S either. So in fact, the only pieces of information we need are the number of data items and the sample mean. So what will our hypotheses look like? Well, H0 is the status quo, which is that mu is 56. H1, based on the question, we're testing for evidence to suggest that the time taken to complete the walk has increased. So that would suggest that mu is greater than 56. Now, you always need to define the meaning of mu. Mu is the population mean time taken to complete the walk. And it is essential that we refer to population mean in our definition here. Now, let's think about the distribution that we have here. X is the time taken to do the walk, and X has a normal distribution with a mu value of 56 and a sigma squared value of 4 squared, sigma equals 4. But of course, the distribution that we work with is the distribution of the sample means, or the sampling distribution of the means, x bar. Now, x bar has a mu value, which is still mu, 56, but its variance is sigma squared over n. So its variance is equal to 4 squared over 19, and its standard deviation, which is the value we end up using, is 4 over root 19. So this is the key piece of information that we need here, and the mu value. So what next? Well, we are looking at a one-tailed test, and it's an upper tail. So we're calculating the probability, or the p-value as it's called, that x bar is greater than our test statistic, which is our value of x, little x bar. So we're working out the probability that capital X bar is greater than 57.4737. Notice there's no need to standardise here. We're not going to gain anything at all from standardising. We can just input this into our graphical calculator. So in stats mode, remember, we want to go distribution, normal, normal continuous distribution. The lower value is 57.4737, and for our upper value, we just need a really large number. So I've gone for 100,000, which is slightly ridiculous, but it gives me some comfort knowing my final answer will be accurate. My sigma value on the calculator is this number here, 4 divided by root 19, the standard deviation of the x bar distribution, and mu is 56, and this gives me a probability of 0.05414 ... I'm going to convert that to a percentage. So that's 5.4% to 1 decimal place. And what do we notice? That is greater than the significance level, which was 5%. So this is not a significant result. We do not have sufficient evidence to reject H0. We do not have evidence to suggest that the mean time taken to complete the walk has increased. So when you're writing your 3 bullet points at the end, those are the 3 things that you need to focus on. We do not have a significant result. We do not have sufficient evidence to reject H0. we do not have evidence to suggest that the mean time taken to complete the walk has increased. So those are your 3 bullet points to jot down at the end as you form your conclusion. So really crucial that we do this comparison here and that we then form our 3-point conclusion after that. So the penultimate example, example number 6. 2 siblings have identical smartphones with an app called Screen Time, which provides the user with statistics concerning the amount of time spent using the screen. So we're looking at the amount of time spent per day on screen. Here are some statistics. Layla believes that X, the amount of screen time, can be modelled by the normal distribution. And for the first part of the question, without doing any calculations, we need to state one feature of the data which suggests that she may actually be correct. Well, there are a couple of ways we can look at this. One very quick standout piece of information is that the median and the mean are approximately equal to each other, which would suggest we have a symmetrical distribution which would fit the profile for a normal distribution. Now, the next part, verify that the values for the quartiles are consistent with this model. So, part B, the distribution we're being asked to use is X is a normal distribution with a mean mu of 56.2 and a sigma squared value of 14.5 squared, which means, of course, sigma is 14.5. Always write that down so you are clear as to what the sigma value is. So the lower quartile should represent the first 25% of the data. So I'm going to work out the probability that X is less than 46.4, and we're going to compare that value with 25%. So we simply go into the graphical calculator in stats mode. Our lower value, just make it small enough, so if you choose some sort of negative value, pick negative 1,000 just to be as extreme as possible. Upper value 46.4, sigma 14.5 and mu 56.2, and you should find you get a probability of 0.24956, which is approximately 0.25 or 25%. So that's the right position for the lower quartile. Now the upper quartile of 66.1, I can work out the probability that X is greater than 66.1 or less than 66.1. If I'm doing the probability that X is greater than 66.1, my lower value on the calculator is 66.1, my upper value becomes a very big number, and I'm expecting the answer to be around about 0.25. And again, if I'd done this as a less than calculation, I'd be expecting an answer of about 75% or 0.75. So again, to 2 significant figures, this is approximately 0.25. So yes, we can verify that there is consistency in the model. Now, part C, we simply have to work out the probability that X is greater than 90, which is by now a very simple calculation on the graphical calculator, and this works out to be a very small number, 0.009875 ... and we want to round that really to perhaps 3 significant figures. Now, quite often these sorts of values are then useful later on in the question, so I'm going to store that in a calculator memory ready for use. So, Layla believes that Y, the amount of screen time used by Wilson per day on his smartphone, might be modelled by Y equals 2x. Use this model to calculate P, Y being larger than 90. So, here's the connection. Y is equal to 2x. So, this question is testing whether we understand the relationship between the mean and standard deviation of X and the mean and standard deviation of Y. So, I'm going to set this information up in a table. So X has a mean of 56.2 and a standard deviation of 14.5. Now, Y is equal to 2x, so the mean and the standard deviation will be adjusted accordingly. So the mean for Wilson will be 2 times 56.2, which comes to a value of 112.4. and his standard deviation will be 2 times 14.5, which is 29. So y will have a normal distribution with a mu value of 112.4 and a sigma squared value of 29 squared. There's the distribution for Wilson. And we've got to calculate the probability that y is greater than 90. So this is again a simple calculation on the graphical calculator. Just need to make sure we enter the correct values. So just make sure you've adjusted your mean and standard deviation appropriately. And you should find you get a probability which is quite a bit larger actually, 0.7800653. Keep that value to hand, and that's 0.780 to 3 significant figures. Now, let's look at the last part of this question. Each night, Layla and Wilson leave their phones on the kitchen table before going to bed. On one occasion, their father picked up one of the phones and said, "This phone has been used for more than an hour and a half." Well, what's the significance of hour and a half? It's 90 minutes. There is a 99% chance that this is Wilson's phone. Use Layla's models for the distributions of x and y to determine whether Layla's father's statement is correct. Now, this is conditional probability. So Layla's father is saying that the probability that it is Wilson's phone, given that it's been used for more than 90 minutes, is 99%. So we need to work out that conditional probability. So all we know is the phone has been used for 90 minutes. There's the condition. What's the probability that it's actually Wilson's phone? Well, we can use the law of conditional probability. I'm going to write that up here in this space. The probability of A given B is the probability of A and B divided by the probability of B. So, putting this into words, this is the probability that it's Wilson's phone and it's been used for more than 90 minutes divided by the probability that the phone has been used for more than 90 minutes. Now, what is the probability that it's Wilson's phone and it's been used for more than 90 minutes? It's 0.7800653, which is what we worked out in this part of the question. Now, what's the probability that the phone has been used for more than 90 minutes? Well, either Layla's phone has been used for more than 90 minutes or Wilson's phone has been used for 90 minutes. It's an or situation. We want to add the two separate probabilities together. So this is 0.780065 add 0.00988. We're not multiplying because we're not asking for the probability that Layla and Wilson's phone have been used for more than 90 minutes. We're asking the probability that either Layla or Wilson's phone have been used for more than 90 minutes. So we want to add together those two separate probabilities. And this gives us a final answer of 0.9875 ... which is approximately 99%. So that does support the father's statement. So, on to our last example. For a period of 20 years until the end of 2017, the parish council have met every fortnight to discuss local affairs. Throughout this period, Mr. Loparts acted as chairperson. The parish council secretaries noted that the mean length of time of meetings throughout this period was 142 minutes. So this is mu, and the standard deviation is this value here, 17.4. How do we know that these are the population values? Well, it's values that have been noted over a really long period of time, 20 years. It's not a sample value, it's a value that's been calculated over a very long period of time. So at the beginning of 2018, Ms. Patel took over as chairperson. At the end of 2018, the secretary stated that he believed that the mean length of time of meetings is lower. So there's an assumption here that will form our alternative hypothesis. The secretary generated a random sample of lengths of times, and the times in minutes are as follows. So here's our random sample. assuming that the length of time of meetings may be modelled by the normal distribution and the variance of the length of time of meetings is unaltered, conduct a hypothesis test at the 5% level to determine whether there is any evidence that the mean length of a meeting has decreased. Okay, let's start from the beginning. What is X? What is the distribution? X is the time taken for a meeting. That's the starting point here. X is the time taken for a meeting. Now, X has a distribution which is normal with a mu value of 142 and a sigma value of 17.4, which means a variance of 17.4 squared. Now, our hypotheses first of all. So the information's in the third paragraph. H0 status quo, mu equals 142 minutes. H1, mu is less than 142 minutes. Mu must be defined and is the population mean length of time of meetings. So really crucial that we write all of this down. We then need to make sure we acquire our test statistic, which is our sample mean, or x bar, which is the sum of these x values divided by the number of values that we have there. So this comes to a value of 130. So that's our test statistic. Now, we need our distribution of our sample means, x bar. So this is a normal distribution which has a mean of mu and a variance of sigma squared over n, if you remember. So its mean is equal to 142. Its standard deviation is the important feature, which is sigma over root n, and that's equal to 17.4 over root 9, which of course is 3. So that is 17.4 over 3, which actually simplifies quite nicely to 5.8. So that's the standard deviation of the x-bar distribution. Now, look at the alternative hypothesis. It's one-tailed, and we're looking at the lower-tailed test here. So we need to work out the probability that x-bar is less than little x bar. So that's the probability that the variable x bar is less than 130. So this then becomes a calculator activity now, substituting the information into the calculator. For my lower value, I'm just going to pick a large negative number to cover all my bases. My upper value is 130. Sigma, the standard deviation, is 5.8 because remember it's the value of sigma over root n, the original sigma, and my mean is mu, which is 142. So this gives me a probability of 0.01927, which we will round and simplify, writing it in the format of a percentage. It's 1.9%, which is very definitely less than the significance level of 5%. So what does this mean? It means the result is significant at the 5% level. We have sufficient evidence to reject H0. And we have evidence to suggest that the mean length of meeting times has reduced. Or decreased. So our 3-point conclusion at the end, with the last point bringing the context of the problem into our answer.